Today we are going to look at 4 types of gas laws that explain the common behavior of gases. Before we get to our gas laws, there is some very important information that we have to be aware of in order to do any kind of calculations that we need. The first one that we mentioned in our previous note is that when we talk about temperature with gases, we use a different temperature scale. So we use something called the Kelvin scale. And the Kelvin scale has a very simple conversion, but it is not a factor. You either are adding or subtracting the number of 273. And the reason that we use 273, this temperature is called absolute zero. And at negative 273, all types of matter on Earth have solidified. Okay, so they've frozen and they are now in the solid state. So a lot of gas chemists use this as the starting point of this Kelvin scale. So if you wanted to do any kind of conversions, you either are adding or subtracting the number 273. Do not multiply or divide. It is not a factor. Lots of times when we carry out gas experiments as well, chemists will use standard conditions. So they'll either use something called STP or SATP. And both of these are standard conditions, just simply the pressure and the temperature change. So STP stands for standard atmospheric temperature and pressure. The temperature is 0 degrees C, and the pressure is atmospheric pressure of 101.3 kilopascals. If they use SATP conditions, this is ambient temperature, which just means this is room temperature, or should be room temperature, which is 25 degrees C. And as a result, the pressure changes slightly down to 100 kilopascals. Commonly, they will ask you to do calculations, and they'll say that now the gas is at STP or SATP, and it will be assumed that you know these conditions. So let's first talk about Boyle's law. And all of these gas laws are named after chemists. This is Robert Boyle, who studied pressure and volume. And just to relate Boyle's law, let's consider an air pump that you have maybe used in the past to inflate a bicycle tire. So as you push down on the air pump, you do something to the volume of the gas inside the pump. And so if you consider this right here, right, if you push down on the air pump, which is right here, you are decreasing, pardon my messy writing, decreasing the volume of the gas inside the pump. If you decrease the volume of the gas, then the pressure of that gas inside this pump now is going to increase, because you have your gas molecules in a smaller space. They don't have as far to go in order to collide with the sides of their container. That pressure, that force is going to increase. So air then flows into the bicycle tire because the pressure inside the pump is greater than the pressure inside the tire. And that is one thing you have to remember. Gases always flow from high to low pressure. So Boyle's law is an indirect relationship. If the volume is decreased, the pressure is increased, and vice versa. And so we represent this as a relationship where the variables are multiplied. Let's try an example with Boyle's law. And we have our formula written down, and we have our variables written to the side. So again, you're going to be dealing with variables that are changing before and after a scenario. So it's good to write down your variables to the side, slot them in as you read through the question. A sample of gas has a volume of 100 mils when the pressure is 150 kPa. Okay, so there we go. We know it's 150 kilopascals. We know that the volume is 100 mils. It says, what is its volume? So this is V2, we don't know, when the pressure is increased to 200 kPa. So when you're doing these questions, make sure that the units are all matching. So I noticed that I'm using kilopascals for my unit of pressure. They're both the same. That's a good thing. Otherwise, I'd have to convert to make them exactly the same. I have a volume in milliliters, which is fine. It doesn't matter if it's milliliters or liters. All that tells me is that when I solve for V2, my unit will be in milliliters as well. we're going to rearrange and solve for V2. So we're going to have P1 V1 divided by that P2 variable. And then we sub in our values. So we have 150 kPa times 100 milliliters. We're dividing by 200 kPa. So my units of kilopascals will cancel out. And consider what you're doing here, right? So you're increasing the pressure, and we know that Boyle's law is an indirect relationship. If I'm increasing the pressure, my volume should be going down. And when you do the math and you do your calculation, it does. You get a volume of 75 milliliters. We need 3 sig figs, so we have to add in a 0 there to round that out. Let's talk about Charles' law now, that is going to relate temperature and volume. So hot air balloons are open at the bottom so that a heat source can increase the temperature of the air inside. When we have ever gone into a hot air balloon or just seen them in action, we know there's quite a large heat source that is heating up those gas particles inside that balloon. By doing that, your gas particles move around faster. They do exert a bit of a pressure, but the idea is that the volume of that gas is going to expand. And when that volume expands, then the air inside becomes less dense than the surrounding atmosphere. And then your balloon floats, much like a piece of wood floats on the surface of the water. So Charles' law deals with temperature and volume of gases. And as long as the pressure and the moles stays constant, then the volume of the gas is directly proportional to its Kelvin temperature. When variables have a direct relationship, we write them as a division of each other. So V1 over T1 is going to equal V2 over T2. And don't forget, with temperature now, we need to be mindful of the Kelvin temperature. So let's do an example with Charles' law. So again, it says a sample of gas occupies 100 mils at 34 degrees C. So let's jot this down. My volume is 100 mils and my temperature is 34 degrees C. Let's convert this to Kelvin right away. So remember that the Kelvin conversion is that 0 degrees Kelvin is equal to negative 273 degrees C. So when you're converting to Kelvin, you're going to just simply add on 273 to your Celsius temperature, which will give me a temperature of 307 Kelvin. And you have to do this now. You cannot do this later because this is not a factor. If this was just simply multiplying or dividing by a factor, it wouldn't matter when you convert. But because you're actually adding on, you have to do this prior to doing your actual calculation. They're asking us what volume it would occupy, and they're increasing the temperature. So, consider your math. If you're increasing the temperature of a gas, it's going to occupy more volume. It's a direct relationship. So that volume we expect to go up. And we're going to add on 273 to convert my temperature to 359 Kelvin. So we're solving for V2 here, which means I'm going to take T2 up and over and get rid of it. So V2 is going to be V1 times T2 divided by T1. So let's sub in. We have 100 mils times T2. Make sure that you're aware of what variables are in the numerator and in the denominator. And I just made a mistake. So it's 359. There you go. 359 Kelvin. And then we're going to divide by T1, which is 307 Kelvin. So my Kelvin unit cancels out. I'm going to multiply this through. The calculator gives me all kinds of digits. I need 3 significant figures. I round to 117 mils. And again, the volume goes up, and that is what we expect. It's a direct relationship. Our third gas law relates pressure and temperature. So this is named after Joseph Gay-Lussac. He was a French chemist. And he came up with the variables, or the relationship between the variables of temperature and pressure. And you may have seen this in action. So consider this scenario. It says, why may your soda can burst open if you leave it in your car too long on very hot days? That's very unfortunate if that happened to you. What a mess inside. Why do closed jars or aerosol cans explode when they are tossed into a fire? So the explosion itself may have, something to do with the actual contents of the can. So if you've got fire and a combustible like hairspray or oil or something like that, that's a totally different thing. But the actual pressure buildup and the explosion is based on gas law chemistry. So it says here, although the liquid inside the soda can has not grown, remember that there's gas particles in a soda can or in a pop can. So the gas has increased its kinetic energy, causing the pressure to build inside that can and burst it open. So Gay-Lussac relates pressure and temperature. And again, this will be true if your volume and your number of moles are held constant. So we assume that, and that we're just looking at the other two variables. It is a direct relationship. If the temperature increases, your molecules are moving faster, they're going to collide more often, your pressure will also go up. Conversely, if your temperature decreases, the pressure will go down. Okay, let's do an example with the Gay-Lussac law. And let's read through and see what's going on. A sealed storage tank contains argon gas at 18 degrees C and a pressure of 920 torr. So let's write this down. I got 920 torr and I have 18 degrees C. And you know what I'm going to do with that temperature right away? We're going to add on 273. We're going to convert to Kelvin because we have to. 291 Kelvin is what I end up with. P2, it says, what is the new pressure? That's what I'm solving for. Oh, in kilopascals. Notice the units aren't the same. If the tank and its contents warm to 32 degrees, must be summertime, during the day. So let's convert to Kelvin. We're going to add those up, and I get a 305 Kelvin temperature. So you got an option here. You can either convert to kPa at the end of this calculation. So you can solve for P2, it'll be in torr, convert then, or you can convert now. It's up to you. I tend to convert now. Okay, so what I'm going to do is off to the corner over here, I am going to convert, and I know I need a unit in kilopascals. I know that I'm dealing with 920 torr. I'm going to equate that to the equivalencies that we learned in the previous lesson, where 101.3 kPa is equal to 760 torr. So again, you either do it now or you do it later. It doesn't matter. When I cross multiply and rearrange, I get a value of 122.6 kPa. And that's what I will use now in my calculation. So if I'm solving for P2, I'm going to take T2, bring it up and over. So P2 is equal to P1 T2 divided by T1. And again, make sure that you're putting everything in the proper spot. P1 is not 920 torr. It is this. We converted. So it's 122.6 kPa. T2 is 305 Kelvin. And then the initial temperature, T1, is 291 Kelvin. So that when I do my calculation, I get a pressure of, calculator says 128.498. How many sig figs do I need? I need 3. So I'm going to say 128 kilopascals as my answer. And that makes sense. The temperature went up during the day. My pressure should go up during the day as well. The last gas law we're going to talk about is essentially a combination of the three prior. So the combined gas law incorporates all three of those other ones. So if you take a look, and if you eliminated the temperature variables, you'd notice here that you're looking at Boyle's law. If you looked at this and you eliminated the volume variables, you'll notice you're looking at the Gay-Lussac law. If you looked at the combined gas law here and you eliminated the pressure variables, and what's left is V1 over T1 equals V2 over T2, that's Charles' law. So in essence, you really only need to learn this one formula, because then you can just eliminate the variables that you don't need. Or maybe, like in this case, you need all of the variables. And if so, you got to be very careful as you rearrange this and solve for whatever we ask. So it says when 3.5 liters of carbon dioxide, so let's write that in, 3.5 liters. And notice now it says SATP. Remember, there are certain conditions that chemists use, and assume you know those conditions in gas chemistry. So SATP has a pressure of 100 kilopascals, and it has a temperature of 25 degrees C, which we're going to convert to Kelvin right off the bat, and that is 298 Kelvin. So when this is heated and compressed, the new pressure is 304 kilopascals, and the new temperature is 109 degrees C. We're going to add on 273. So they're really heating this up. And we get 382 Kelvin. So we want to know what is V2. And so we take our combined gas law, and we need all the variables, and we're going to rearrange to solve for V2. So let's just set it up here for you, and then we'll get you guys to calculate this on your own. So if I want to solve for V2, I got to move P2 out of there. I'm going to bring it down, and I'm going to take T2 and cross multiply it up into the numerator. So that V2 is equal to P1 V1 times T2 divided by T1 and P2. You have to be very, very careful here that you're putting the right variables in the numerator and the denominator. I'm going to let you insert that, calculate this for yourself. The answer that you should be getting here, rounded to sig figs, is 1.5 liters.